When we think of concrete, we think of something that's super strong, but also really brittle, right? Something that just shatters. But what if it didn't have to be that way? What if concrete could be engineered to bend, almost like a piece of metal? Well, today, we're diving into a material that does exactly that: engineered cementitious composites, or ECC for short.
I mean, this is the fundamental question. For as long as we've been building with concrete, its Achilles heel has always been its brittleness. Under tension, it cracks, and that crack leads to catastrophic failure. ECC is a material that was designed, right from the micro scale, to solve that exact problem.
And here it is, the punchline, right at the start. Just look at these numbers. This is the tensile strain capacity, basically how much it can stretch before it snaps. Normal concrete gives up at about 0.01% strain. ECC, it can get past 2%. And I want to be really clear here, that is not a 10 or 20% improvement. We are talking about a more than 200-fold increase in ductility. This isn't just a better concrete, it's a completely different kind of material. So what is ECC officially? Well, it's a composite that's been specifically engineered to act more like a ductile metal when you pull on it. And the key term you're going to hear a lot is pseudo-strain hardening. All that means is that, unlike regular concrete, which fails the second it gets its first real crack, ECC actually keeps getting stronger while forming this whole network of tiny, tiny micro cracks. Okay, so to really wrap our heads around what makes ECC so special, we have to look at how it behaves under the one condition that is concrete's mortal enemy: direct tension. This is where all the magic, or, the carefully engineered science, really happens. Now, for any of you who actually work in a materials lab, this is a super important point. The standard tests we use for concrete, like the splitting cylinder or four-point bending, they're all designed for brittle materials. If you use them on ECC, you're going to get results that are not just misleading, but non-conservative. They'll actually underreport the material's strength. The only way to see what this stuff can really do is with a direct tension test. And honestly, the fact that you can even do that test without it shattering is a testament to ECC's built-in damage tolerance.
This stress-strain curve tells the whole story. At first, it behaves just like concrete, stretching elastically. But then you get to the first crack, and everything changes. Where concrete would just catastrophically fail, ECC enters this incredible strain hardening phase. It forms a whole series of fine microcracks, and, this is the critical part, it keeps taking on more load. It only starts to truly fail after it's hit its absolute maximum strength.
So how in the world does it do that? Well, the secret is all in the micromechanics. The mix is full of these tiny polymer fibers. When a microcrack starts to form in the cement, these fibers act like tiny bridges across the gap. They're designed with just the right amount of grip, strong enough to transfer the load, but also able to slip just a little. This controlled slip prevents any one crack from getting too wide and forces new microcracks to open up somewhere else instead. All right, so let's see how this all builds on itself. This incredible tensile performance doesn't just exist in a vacuum. It creates this massive ripple effect, and it dramatically improves how the material performs under more complex, real-world scenarios, like bending or flexure and shear. And here's a quote from the research that's so important for any of you working in this field. It's easy to see something bend and just assume it's got great tensile ductility. But this quote reminds us that true tensile strain hardening is the cause. The fantastic performance you see when you bend an ECC beam is a direct result of its fundamental behavior when you pull on it. It's a key distinction. And the practical benefit is just stunning. In bending tests, the flexural strength of an ECC beam can be more than 3 times its initial cracking strength. Just think about that for a second. The beam gets significantly stronger after it has already started cracking. For a structure in the real world, that's the difference between a sudden catastrophic collapse and having a built-in warning system. Okay, now look at this. Let's talk about shear. On the left, you've got plain concrete, which has basically zero shear strain capacity. The middle bar is our standard steel-reinforced concrete, which gets us up to almost 2%. But then look at the bar on the right. That's ECC, with no steel reinforcement at all, and it has an even higher shear strain capacity. The material itself is more ductile and shear than concrete with a bunch of steel rebar in it. And the reason for this amazing shear performance is actually pretty simple when you think about it. shear failure in brittle stuff like concrete is really just a failure in diagonal tension. So because ECC is so incredibly ductile in tension, it handles shear by just forming a network of tiny diagonal microcracks instead of one big catastrophic fracture. The bottom line is, by solving the brittleness problem in tension, you automatically create a material with phenomenal shear resistance.
Now, it's really important to get this. ECC isn't just one single recipe. It's more like a platform technology. You can think of it as a whole family of composites where you can precisely tune the properties for a huge range of different applications.
This table really shows you the incredible versatility we're talking about. You can tweak the mix to create an ultra-lightweight version for fireproofing that's literally less dense than water. Or you can go the other way and make a high-strength version for blast resistance with compressive strength over 200 megapascals. But look at the one thing they all have in common, that high tensile strain capacity. That's the signature that makes it ECC.
And this is really the ultimate engineering achievement here. For decades, with concrete and other cement materials, getting higher compressive strength always meant you had to sacrifice ductility. The stronger it got, the more brittle it became. ECC completely breaks that link. It lets us design materials that have crazy high compressive strength and are also incredibly ductile. So, let's wrap this all up. For you, the people who will be the next generation of material scientists and structural engineers, what's the big picture here? What's the main thing to take away from all this? It's truly a paradigm shift. For more than 100 years, designing with concrete has been an exercise in managing brittle failure. We add steel rebar to contain the damage we know is coming. ECC lets us move away from that, purely defensive strategy. For the first time, we can design structures using a cement-based material that is inherently ductile and resilient, right from the very beginning. And that really leaves us with one last big question. By engineering this incredible ductility into the most common building material on the planet, what does that unlock? What new, more elegant, more resilient structures can we now even dare to imagine and create? That's the challenge, but it's also the opportunity that ECC presents to all of us. Thanks for joining me for this explainer.